This is FE Peer Review. The date is April the 17th, 2022. Peer review of Brian's Logic Blackpool Swan Revisited. There is a current and ongoing discussion between Brian's Logic, Ranty, and perhaps some others regarding the famous Blackpool Dowcrag photo. Brian has created a model which he is using to analyze that photo, and I am analyzing his analysis. Hope you enjoy. Brian, on April 16th, 2022, you did a video called Blackpool Swan Revisited. We see it here on the screen. This video was an analysis of this photo here, Blackpool Tower with Dowcrag in the background. You used a tool called GeoGebra. You recreated to scale an observer, Blackpool Tower, and at the left, Dowcrag. Your image is as orthographic. There is no perspective in this image. You drew from this image and your analysis some conclusions, namely that the photo supports a hypothesis that the Earth is flat. We're going to look at that. But first I want to say that if you can use an orthographic image and analysis and draw a definite conclusion, then I can do the same. I can also use the same orthographic image and the same type of analysis and also draw a conclusion. You cannot dispose of my conclusion simply because it's orthographic. If orthographic worked for you, then it works for me. So what I've done is I've used the same tool, GeoGebra, and I am recreating what you've got here in your analysis. And I'm including a couple of points that you did not include in your analysis that I think are the primary points and which several people have requested. Namely, what we are most interested in this photograph is, if we look where I'm circling the mouse, a line of sight from the observer, a straight line of sight to the top of Dowcrag. We're curious as to where that would intersect the tower, and also a straight line of sight from the observer to the top of Blackpool Tower. We're going to examine those two lines of sight using the same analytical approach and the same tool that you used. I want you to see that I have in fact correctly copied your model so that we can agree that I am using the same information you are. Here is your video. From your video, a still taken at 6:15. Observer 6 meters, 19.3 kilometers from Blackpool Tower. There's your graphic. Now we're going to go over to GeoGebra. And here I've put it in on the left. I'm going to zoom in. We see that we're at 193. And there it is coming up. Sorry it takes so long to zoom, but I want you to see precisely what I've done here. And let's get rid of this. You can see that the height is 0.06, just as you've got on yours. So that's our observer location. Here we see your Blackpool Tower. Now there is an error in your data because this is the height of the tower itself measured to the ground level at its base, not to mean sea level. But I am going to replicate your model exactly as it is, including the error, so that we're comparing apples to apples here. I may go back at the end of this video, if it's not too long, and make a second version with those corrections included. So there's yours. Now we'll move to mine. And we will zoom out and across. Sorry this takes so long, but we will zoom out. So, okay, there's my Blackpool Tower. We're at the 0 at the bottom and just under 1.6 at the top. Just under 1.6 at the top, 1.58. So those match. And here we see your Dowcrag, 778 meters at the minus 644 mark. And there we are at the minus 644 mark, just under 8 meters high, 778, the scale's on the right. So those are the 3 locations of interest. I am now going to draw a straight line from the top of Dow Crag to the observer location. And then we will see where it intersects Blackpool Tower. We now have our line, a straight line of sight from our observer to the top of Dow Crag, and we will now move to the point where it intersects the tower. What we see is that line of sight passes above the top of the tower. So a straight line of sight from our observer location to Dow Crag, based on a flat plane, passes above the top of the tower. Now, does that match what we see in the photo? No, it doesn't. What we see is that the line of sight to Dow Crag actually passes below the tower. So this does not match what we see in reality. I will now draw a line from our observer point through the top of the tower and continue that line on to see where it intersects Dow Crag. To do that, I'm going to use the tool called Array. Array is simply a line with the starting point, and the second point is along that line's length. Our starting point will be our observer location, our second point will be the top of the tower, and the line will continue on to Dow Crag. Here we are at the tower. I will now move the line up to the point where it intersects the tower. And we now have a line from our observer point to the top of the tower, and we will see where it intersects Dow Crag. Okay, here we are at the intersection of our line and Dow Crag, and what we see is that a line from our observer through the top of the tower is below the top of Dow Crag, based on a flat plane. Is that what we see in the photo? A line from our observer location passing through the top of the tower, in fact, goes above the top of Dow Crag. So the photo and the analysis don't match. Now, Brian, I used the same setup that you used. I used the same tools. I used the same distances and heights. I drew the two rays, the two lines of sight that were the critical information we were trying to seek, which is the line of sight from the observer past Blackpool Tower to the mountain. Your analysis does not match what is seen in reality. So, Brian, I have shown that your model is flawed because it does not accurately reflect what is seen in the real-life photo. Consequently, the conclusions you've drawn from it, and you have drawn some conclusions which we will hear in a moment, aren't supported by solid evidence. Your analysis is flawed, as we saw, so the conclusions you've drawn are still lacking support. I suggest you go back to your analysis and try to figure out why it does not match what is actually seen in the photo. There could be a number of things you might want to look at. You might want to look at correcting the distance to Dow Crag from Blackpool Tower. You might want to look at correcting the height of Blackpool Tower because you did not consider it the base elevation above mean sea level. You also didn't consider the height of the observer. You've got the ground surface the observer standing on, but you're going to want to raise the height a little bit more because the person has not got their eyes on the ground. They're about 2 meters up from the ground surface. You might also need to consider the flat plane as your baseline. So I encourage you to go back to your model and explore where the errors entered into it and why it does not match what is seen in the photo. Now we will go back to your video and listen to your specific claims based on your analysis, which is questioned since it is clearly in error, not matching the photo.
And this absolutely proves that the Earth is flat. You know, there's no way around that. The Earth is flat. This is exactly what I said. And there's not even and this is all autographic, there's not even optical drop or visual occultation being taken into account here. What I might do is when I get to learn how to use the 3D calculator in this a bit better, I'll try and maybe model it out in that, just to show the optical drop and visual occultation.
Brian, you mentioned optical drop and visual occultation. When you do refine your analysis further, please explain what those two are and give precise, measurable, quantifiable means for other people to recreate them in their own observations. This is the essence of the scientific process, enabling other researchers to verify or check your work by doing the same work themselves. So please, we need details about the numbers, the angles, whatever it is that's involved in optical drop and visual occultation. Thank you. Now we will continue to listen to what you were saying about your analysis disproving the globe Earth.
But the point is that there you go. I mean, all their claims debunked. You know, all their claims. You know, so there's a 52-mile distance between these two, and this is 19.3 kilometers from, or 12 miles from the Blackpool Tower, and this is 64.38 kilometers from Blackpool Tower to Dale Craig. So it's debunked. There's no way around it. All their claims on that day is debunked. IONLES can copy this in this GeoGebra. So there you go. I don't know what to say. I mean, exactly what I said was true.
Unfortunately, it wasn't, was it? Because your very own model, when recreated carefully, did not match what the photo showed in reality. So your model is flawed. Therefore, your conclusions are questioned. I've decided I will go ahead and go back in and adjust your model to see if we can correct some of the obvious small errors that are in it and see what that result gives. I'm going to do it first, keeping a flat ground plane. I'm going to adjust the distance to Dow Crag from Blackpool Tower, and I'm going to adjust the height of Blackpool Tower to account for mean sea level. First, let's get the correct distance from Blackpool Tower to Dow Crag. We see Dow Crag here in the image, and the red line is the path I've traced to Blackpool Tower. Dow Crag at the top, Blackpool Tower at the bottom. Looking at the properties of that line, we see that it is 61.9 kilometers long, or 38.5 miles. So we'll make a quick note of that. And since we're in Google Earth, we will take a moment to look at the base elevation of Blackpool Tower here. So tower heights, building heights, are measured from the ground surface at their center, not from mean sea level. If we look at Blackpool Tower, the ground to its west has an elevation of 26 feet, the ground at its right an elevation of 30 feet. So that puts it at around 28-foot elevation. That's roughly 8.5 meters. So the base of Blackpool Tower is 8.5 meters. And while we're at it, let's double check the height. We see the Wikipedia page for Blackpool Tower here, and it gives us a height of 158.1 meters. So we'll make a note of both those numbers, and then we will correct the model. So here we are back at the model. We've got Dow Crag on the left at about 64 kilometers from Blackpool Tower. The correct figure is 61.9. So we need to move that line over to 61.9. Would be right about here. So that's our new Dow Crag location. Now we will proceed to fix the height of Blackpool Tower. Instead of 1.58, we want 1.667. So there's our new height for Blackpool Tower. Now let's redraw the line that connects Dow Crag to our observer location using the corrected model, which is still based on a flat plane. So we have a line going from Dow Crag Okay, we're zoomed in here, and we're going to bring it down to our observer location. And now we will see where that line intersects Blackpool Tower. First, just to make sure we're looking at the correct line when we get to Blackpool Tower, we will note that the new line is above the old one. So when we get to Blackpool Tower, we need to be looking at the upper line. All right, here's the top of the corrected Blackpool Tower, and we see that the line of sight, as shown in the model, from the observer to the top of Dow Crag is above the top of Blackpool Tower. The line of sight from the observer to Dow Crag is above the top of Blackpool Tower according to the model. However, according to the photo, it's below the top of Blackpool Tower. So the correction that we made to the dimensions, the heights of the objects, did not bring it into conformance with the photo. Now let's go back and look at what happens when we draw a line from the observer through the top of Blackpool Tower to Dow Crag. I'm going to go ahead and delete the lines for Blackpool Tower, just so that we don't get confused which lines we're looking at. There's kind of quite a few lines on here right now. Okay, we'll do what we did before and use a ray originating from our observer location and passing through the top of the corrected Blackpool Tower in the direction of Dow Crag. Let's zoom in here. Okay, I'm selecting a ray starting at our observer location. Well, we are passing through the top of the corrected height for Blackpool Tower. There is our ray. We will now see where that is relative to the top of Dow Crag. Okay, here's the corrected Dow Crag location, and we see our ray passing below the top of Dow Crag. So, according to this model, a straight line of sight from the observer location through the top of the corrected height of Blackpool Tower passes below the top of Dow Crag. However, that is not what we see in the photo. We see that the line of sight from the observer through the top of Blackpool Tower passes above the top of Dow Crag. So fixing those dimensional errors in the model, the height of the Blackpool Tower and the distance of Dow Crag from Blackpool Tower, did not change our conclusion. The model is still flawed in the same way it was before, by slightly different amounts, but the same flaws. So there must be some other cause for the model being so far from correct. What we're going to look at next is what happens when we account for drop due to Earth curvature. We're going to use as our high point, you might say, we're going to put at our observer location, and we're going to use drop dimensions taken from an Earth curve calculator and move the bottom of Blackpool Tower and the bottom of Dow Crag down those distances. So we're now back at Walter Bisland's Earth curvature calculator. I've put in target distance 19,600 meters, 19.6 kilometers. I've got refraction set to 0, although that doesn't actually affect our results. And down here we see drop, 30.15 meters. And if we look at the diagram below, we see that drop is measured from the ground at the observer location, straight out and down to the ground at the target location. So that's what we're interested in. How much has the Earth curvature dropped the base of Blackpool Tower at mean sea level? And the answer is 30.1, so we will put that in our model, and then we will do the same for Dow Crag, and I will type in 81,600 for Dow Crag. And for Dow Crag, we get a drop of 522.5 meters. We're now back at the model, and we will make those adjustments. I have deleted the old Blackpool Tower and old Dow Crag that were not correct in their dimensions and heights. I've left the ones that we put in last time, and we're going to put a new version of each with their bases set according to the Earth curvature drop. For Blackpool Tower, that would be 30 meters down. So there we see our new Blackpool Tower. The base is 30 meters down from the one we drew previously, and of course the top is 30 meters down because the overall height remains the same. We're now at Dow Crag. We need to drop Dow Crag by 522 meters, according to the Earth curvature numbers. So for Dow Crag, we had a total height of 778 meters, and we need to drop the base by 522 meters. So we start down 522, which is about there. Total height of 778 would bring us to 226, right about there. So that's our new Dow Crag location. So what we see as far as Earth curvature is, starting at the right, our observer location, that would be 0. As the distance from the observer moves to the left, we have at Blackpool Tower a drop of 30 meters, and then continuing on to Dow Crag, a drop of 522 meters. That's now in the model. So now we will draw the lines of sight that we drew before and see what that gives us. I'm going to erase the current lines of sight just to keep the model a little bit cleaner. Here we are at Dow Crag. The bottom of Dow Crag, mean sea level, is down here where I'm circling the mouse, and the top is where I'm circling the mouse. And we will draw our line segment from the top of Dow Crag towards our observer location. There we are at the observer location with our line in place. We will now move over to Blackpool Tower and see where this line intersects Blackpool Tower. Okay, we're at Blackpool Tower. Keep in mind that the dropped Blackpool Tower is what we're interested in. That goes, the base of it would be where I'm circling the mouse, and the top where I'm circling the mouse. And here is our line of sight from the observer location to the top of Dow Crag, and it passes well below the top of Blackpool Tower. How does that compare to the photo? Here's the photo. We're looking at the line of sight from the observer to the top of Dow Crag, and we see that indeed it does pass below the top of Blackpool Tower. Now, it's not the same amount as we see in the photo here, but do keep in mind that we have not included atmospheric refraction in our calculations and in our model. However, the relationships are correct. The line of sight from the observer to Dow Crag is indeed below the top of the tower, as seen in the photo. So that's a pretty good match there. Now we will do the same as before. We will draw a line from the observer location to through the top of Blackpool Tower and see where it rests when it reaches Dow Crag. All right, we are back at our observer location. We are going to draw a ray, as we did before, with its origin at our observer. That ray is going to go through Blackpool Tower and on to Dow Crag. There's our Blackpool Tower, and keep in mind we are using the one that extends from D through E, the lower one. There's our ray. We will now go check out Dow Crag. And there's our ray, the upper line, and it is well above the top of Dow Crag. So the line from the observer through the top of Blackpool Tower passes well above Dow Crag. How does that compare to the photo? Here's the photo. We are looking at a line that goes from the observer through the top of the tower, and yes, indeed, it is well above Dow Crag. So, conclusion. When we apply the corrections due to Earth curvature, we find that the model, the orthographic view made in GeoGebra, which you yourself, Brian, used for your video, when we apply those corrections to it and do the analysis the way you did the analysis using an orthographic projection, we find that the Earth curvature corrections bring the model much closer to matching the photo. So Brian, you got something to answer there. Now I know you will probably bring up visual occultation and that was some other phrase you used. Anyway, you're going to need to explain what those are in a manner that can be quantified so that they can be applied to the model and be shown to match the photo. If you can't do that, then you haven't got a leg to stand on. So that's your job, Brian. Show that your visual occultation thing actually works and makes what we see here match the model. As it stands, Earth curvature does the job. So, ball's in your court. Have fun. This is FE Peer Review. I hope you all enjoyed this. You know the routine. There's a like button down there, and there's lots of room for comments. Have a great day, everybody. Bye-bye.